All right. Can everyone hear me fine? Okay, good. So the whole talk's not going to be all about history. It's going to be about a few different things. Historical perspective on diffusion anisotropy alone, not all of diffusion weighted imaging. The second topic was research utility, which I'm actually not going to talk about because the whole conference is going to show you a whole bunch of utility of diffusion anisotropy. So instead, I'm going to change the title a little bit to clinical challenges and new MRI sequences. And so it won't all be historical stuff. It'll be where are we going and what are some things that we can do on the acquisition side to yield some more information that we may not have heard about earlier today. But the last time I gave an invited talk, Flavio, who invited me to give this particular talk, sent me this text, and next time, give better talk. So I'm hoping I don't end up in the same situation after this talk, but you never know. We were there for this conference, a spin through the history of restricted diffusion MR, which was a conference put together by Derek Jones. And it was in honor of Dr. John Tanner of Statistical Tanner fame, who we use his sequence we use all the time, and you can see it behind him there while he was giving his talk. And this website, if you go to Psychology in Cardiff, you can see all the talks that were given, and there you will really get the history of diffusion MR because all the pioneers that gave talks. And then it ends actually with a lot of the latest younger people that have new ideas and new topics as well. So I recommend you to go look at that website and check out the talks. All right, so we've heard lots today that the water molecule is typically imaged in MRI, and what makes water interesting is its interactions with proteins, with membranes, and it's the microstructure information, as we keep hearing over and over again, that leads then to being able to delineate white matter tracts, detect acute stroke, and so forth. So it's really important to keep in mind that even though we have very low resolution in our images, that what information we're getting is at the microscopic level, right? The water molecules are interacting at the microscopic level, and we can think of MRI as our kind of in vivo microscope to the human brain. So the three questions we're going to talk about today are what is the relationship between various neural microstructural elements and water diffusion? And this will involve a bunch of history, I guess some old papers. I guess I'm at the end of the day, so I guess I'm the old guy talk. And then diffusion anisotropy, is that property has been very useful for research, but why has it been limited in the clinic? And then what other diffusion acquisitions might be useful for brain studies? Okay, and it won't be an exhaustive list, of course. I only have half an hour to cover all that, but that's what we're going to cover today. So let's start off with the source of diffusion anisotropy. All right, so the first thing you have to do is forget that celery petioles have high anisotropy. All right, so unless your subject looks like this with the head of celery, you can see here that, where's the mouse? Oh, that's a pretty tiny little arrow. I don't know if anyone can see it, but you can see that the petioles, or the bright dots on the outside, have restricted diffusion perpendicular and faster diffusion parallel, right? So that gives you an indication right off the bat that diffusion anisotropy is not a very specific measure of, right, just from that alone. But we'll get on to, hopefully we'll be able to get information out of it that can give us specific information about microstructure. This was the first diffusion workshop in June of 1990, Future Directions in MRI of Diffusion and Microcirculation, and it was in Bethesda, Maryland. And you can see here the chairman was Denis Lebihan, and my PhD supervisor went to this meeting and came back and said, oh, we have to start doing diffusion. I arrived in September of 1990, and yes, I realize that that's 27 years ago. And that was my job, was to get involved in getting diffusion MR going at the University of Alberta. This was one of the abstracts by Michael Mosley in that syllabus, and he talks about the ordering and hindering of the water diffusion probably along the axis of the individual neurofibrils as well as potentially the myelin sheath itself. Okay? And this led to the seminal paper in 1990, which really demonstrated it quite nicely in white matter that diffusion was anisotropic, and this was in the cat. And this was really the paper that really got everything rolling. But there were inklings of that back in 1987 in this paper by Thompson et al. In the human brain, where they saw that there was differences in diffusion coefficients in different parts of the brain, frontal white matter versus visual radiations, and they postulated that it might be due to the degree of myelination or perhaps due to anisotropic diffusion. So they kind of recognized, as early as 87 that there might be something up with this. And then this was shown also in human brain in 1990 by Chenevert colleagues here by looking at, they saw different diffusion coefficients as they went from the front of the brain to the back of the brain and talked about anisotropy. All right, but what were the origins of this anisotropy? This was a review article in 1991 by Denis Le Bihan that talks about, well, for sure diffusion's anisotropic in white matter, but there's still controversies regarding the origin. I like the still part because it was just, published a year earlier, and here we are debating it 27 years later. You can see my little scribblings when I was a PhD student, what I'm trying to solve here on this. And then below, he talks about decreased mobility through the successive lipid bilayers of myelin. You can see that there might be facilitated transport that's favored by the intraaxonal microstructures such as neurofilaments. So really, there's lots of different elements that were brought up that potentially could contribute, but there was no answers to that. Even if you looked at this paper in 1991 that talked about color mapping of myelin fiber orientation, the first figure shows these myelinated axons, and the figure caption says diffusion in myelin. So really, that was the prevailing theory at the time, that myelin was really the cause of all this anisotropy. But it hadn't really been shown or proven at that point. And so really what I became interested in was, and lots of other groups as well, is what are the relative microstructural contributions to this anisotropic water diffusion. So you have the myelin sheath, the axon membrane, the cytoskeleton, lots of things that are ordered and lengthy that could make axial diffusivity greater than radial diffusivity. And this could be evaluated in a bunch of different models. So the models that I looked at, even though I'm in Alberta, which is very far from the ocean, we looked at garfish, which are these handsome-looking fish here at the top, and the squid giant axon. And these papers were back in 1994 in MRM, magnetic resonance in medicine. It's also the year that Peter Basser introduced the tensor formalism for diffusion. And so why did we pick this weird fish, the garfish? Well, because it has this long nose. And what's in that long nose is a non-myelinated olfactory nerve, a myelinated trigeminal nerve, which is a peripheral nerve, and a myelinated optic nerve here, which is a central nerve. They all have different axon diameters and so forth, and you could measure the diffusion properties and compare them and see if you would predict that you would have no anisotropy in this non-myelinated olfactory nerve if myelin was the key. So if you measured then the parallel diffusion coefficients, or the apparent diffusion coefficient, parallel over perpendicular, back then we didn't have the tensor formalism, so that's what we did, measured parallel and perpendicular, because we could align these nerves along our gradients. And you can see that it's highly anisotropic. And in fact, it's more anisotropic than the other two myelinated nerves. Right? So that kind of proved that you didn't need myelin in order to cause anisotropy. So that was the garfish. So you could look at other samples like this non-myelinated walking leg nerve for the lobster, myelinated sciatic nerve from a frog, as well as a myelinated fornix in a human measure. And I've introduced the FA values here above. You can see that the FA values are 0.56, 0.68, 0.49. So really these are all about the same. Okay? We have different axon diameters, we have myelin, we have no myelin, yet there's still a high degree of anisotropy, suggesting that axonal membranes themselves were sufficient to cause a high degree of anisotropy of water diffusion. Okay? So, but what about that neurofilamentary lattice that's in there, right? So all these axons have neurofilaments, microtubules. Well, the only way you can evaluate that is by making a measurement where most of the water molecules aren't hitting a membrane, right? So what you could look at is the X-sized squid giant axon. So in this case, the giant axon is about 300 microns, the ones that we got shipped to us from Texas. And the diffusion of water over the diffusion times we were using, our root mean square displacement might be around 9 or 10 microns, something like that. So a lot smaller than 300 microns. So sure, some of the water molecules that we measure are going to hit the membranes, but most of them aren't. And when you measured the parallel and perpendicular diffusion coefficients, you could see that they were nearly isotropic. There was some slight anisotropy, but not a lot. This was followed up by a different group that looked at the lamprey axon. That's this little circle there. It's only 40 microns, and they found complete isotropic diffusion in their sample, suggesting again that if you don't have membranes in place, the neurofilamentary lattice isn't doing anything. The other interesting thing that we saw from these two studies was that these were done at different temperatures, and if you look at these black bars, which is the diffusion coefficient of pure water, you can see that the diffusion coefficients within the axon itself is very close, or about 80% of the diffusion coefficient in pure water. And that's true at both temperatures. Okay? So that means that the water diffusion in axoplasm is very rapid. So the conclusions from this study was that the neurofilamentary lattice contributed very little to diffusion anisotropy, that membranes confirmed to be the major player coupled with that previous Garfish work, and that the water diffusion was very rapid in the axoplasm. So the inside of the axon, the water is actually moving around very rapidly and sort of like a gel. All right, so others have, and in that same lamprey spinal cord paper, they looked at different parts of the spinal cord that had different degrees of axon diameter and different packing density. And what they showed was as the axon diameter increased or the packing density decreased, the degree of anisotropy went down. And these were all in non-myelinated regions of the spinal cord, again confirming that the axon density and the membrane density was really the key to creating this anisotropy. All right, so that's all fish and lamprey and so forth. What about human tissue? So this was a study that we did where we took advantage of the fact that temporal lobe epilepsy patients were going in for surgery and that we could get a piece of the fornix during surgery. And so what we did is we did DTI pre-surgery, and then we're able to measure anisotropy and other parameters. Then we did electron microscopy of that piece of fornix that was extracted during the temporal lobe epilepsy surgery and correlated the fractional anisotropy and versus a bunch of different metrics, myelin, content, and so forth. And what came out was that the FA was correlated to the cumulative axon membrane circumference. So the more membranes that you have, the higher the FA was. The less membranes you had, the lower the FA was, confirming exactly what we just saw on the previous slide on the lamprey spinal cord. But this was in human tissue. And each of these dots is 11 different patients. So that was kind of interesting. But does that mean that that myelin doesn't have an effect? Well, if you look at these two columns, these are mutant mice. One of the columns is mutant mice. And these are the FA maps from these 3 different studies. And the question is, which column has myelin? Well, they look pretty similar, but it turns out this one has no myelin, this one does have myelin. And if you actually make the measurements, there is about anywhere from a 10 to 20% change in the anisotropy parameters when you lose the myelin. But it's a small modulation. It's not small. It's still a pretty sizable modulation, but there's still significant anisotropy that remains. Right? So myelin can modulate the degree of anisotropy, but it's not the main reason for it. Now, why are we interested in anisotropy? Well, because we want to measure when things get bad and degenerate. And so in this example where you have degenerated frog sciatic nerve after a tie injury, the anisotropy goes down. And it's those kinds of links that we're all interested in doing in vivo. So this really got a real kick by Victor Song in 2003 when he introduced this kind of idea. If you look at the eigenvalues or the parallel and perpendicular diffusivities, that in this retinal ischemia model, that the parallel diffusion would go down early, and that corresponded to histological evidence of axonal degeneration, but the perpendicular diffusion didn't change at all. Later on, the perpendicular diffusion would go up, and that was linked to demyelination. So he came up with this kind of hypothesis that the parallel diffusivity was more sensitive to axon damage, and the perpendicular diffusion was more sensitive to demyelination. And that's where this kind of came from. Of course, in this example, he knew when he was doing the injury, and in many cases, we don't have that luxury. Okay, so that makes it a little more difficult for us to interpret specifically. Lots of other things can cause ADC perpendicular to go up or ADC parallel to go down. Now, what about in humans? So to follow up from Victor's work, well, here are epilepsy patients that get the corpus callosum cut in order to prevent transmission of the seizures, and it's color-coded by FA. So you can see at 8 days and 60 days after surgery, corpus callosum's cut, and the FA is blue, very low FA, but it looks the same between 8 days and 60 days. So the question is, are these the same? No. So at 8 days, parallel goes down, ADC perpendicular doesn't change. I'm not showing you the data from that, but it's in the paper. And at 60 days, ADC parallel is the same, and ADC perpendicular goes up. So exactly what Victor Song showed in the retinal ischemia model is also evident here. So you can also go beyond the tensor to identify axon degradation. We've heard this earlier, when we saw this slide by Flavio earlier, where what you'd like to know is if you have areas of fiber crossing and one fiber is affected and the other one isn't, can we pull that out? Well, Luis Concha at ISMRM just in 2017 here, just a couple months ago, did a retinal ischemia model just like Victor did, and he wanted to see if he could tell one degenerating fiber at this crossing region relative to the other one. So what he did is he did some imaging with spherical deconvolution analysis, and in the control animals, both nerves are intact, and you see these nice two populations as expected. And then in an ischemic model, you start getting a degenerated nerve on this side, and the intact nerve is still fine. But if you look at the optic chiasm, this one's fine, but the crossing fiber that's been degenerated is now affected. So showing that you can get this very selective, pull out selective injury to one particular fiber bundle by using these more sophisticated methodologies. All right, and if you want to learn more about the actual history, there's lots of articles in these articles here in the books. All right, so that's a really rapid overview of some of the basics or history of diffusion anisotropy, and there's clearly a lot more work, and I invite you to go look at all the original articles by lots of other groups in those chapters. So what about issues with clinical utility? All right, so let's make a distinction. There's diffusion-weighted imaging, where you only need 3 different directions, and then you can calculate an MD map, and the scan time is very rapid. So this is what's often done in the clinic. You can also do DTI very quickly. If you just do quick 6 directions, you can get it off in a minute and a half, couple minutes. But usually you do more directions, more shells, etc., and it could take as long, I guess, as 60 minutes if you're doing the connectome. But you can get a lot more information out, obviously. So we know that diffusion-weighted imaging is in every brain MR exam. It's routine. You can detect stroke, and there's other clinical uses as well, tumors and abscesses, and et cetera, et cetera. So what about DTI? So I know this is a few years old, about 3 years old, and this is not published. It's just a very ad hoc, informal survey. I basically emailed 15 neuroradiologists around the world and kind of asked them their opinions of, did they use DTI? What did they use it for? And if not, why didn't they? And it turned out that 13 to 15 of them used DTI clinically for certain cases, and the main use was for pre-surgical mapping to guide brain surgery. So they were looking for the best surgical approach, assessing track locations to avoid injuring them, to predict potential side effects. But even then, most of them said, maybe a handful of cases per week. So despite the hundreds or thousands and thousands of papers that we have on DTI in research, it's really not translated to the mainstream. A few other centers also used it for degenerative disease and a few other things, but it really isn't being used a lot. But there are some examples in literature where this might be useful. For example, this paper here was looking at temporal lobe epilepsy surgery, and the goal was to avoid cutting the optic radiation to avoid causing visual field defects. And so what they did is they did some pre-surgical DTI in all these people. Post-surgery, they looked at where the resection was taken, and you can see here some of this optic radiation was pulled out of there. And then if they correlated the amount of damage to the optic radiation with the visual field defect, they saw a pretty nice correlation. So there's maybe some distinct applications that this could be very, very useful. On the other hand, this paper here just 2 years ago basically gave some data of a brain tumor patient to 8 worldwide teams and said, use your tractography algorithms and show me the pyramidal tract. Okay, so each of these, there's the tumor there, and you can see these are 8 different reconstructions. And we saw this earlier today. Depending on what algorithm you use, you can get very different tracks. So what's the neurosurgeon to do in this case? All right. Obviously, the core, this little stump here, is the same as everywhere else, but what do you do with this big mess of fibers here? All right, so there's not a lot of consistency for this. So what are the barriers to the clinical use of DTI? And this is the neuroradiologists in responding to my survey. One was the time constraints, longer scans, excessive time for processing, legacy of qualitative evaluation in radiology. You know, the FA maps look pretty similar. You saw the genetic FA maps I showed you earlier. They look pretty much the same. You need to quantify them to pull out the changes. There's inherent limitations of the methodology in terms of spatial resolution. It's noisy data. How accurate is it? Is it valid? And there's really no standardized method. And we heard a lot about this in terms of acquisition and post-processing. You know, there's lots of things you can vary, TRs and Ts and field of views and slice thickness and cardiac gating and inversion recovery and et cetera, et cetera, et cetera. All these things are going to have an effect on your image quality and the absolute numerical value of your DTI parameters. They're not all going to be the same, right? And then an analysis, this is a review article by Derek Jones and Mera, and published in 2010, and they had 25 pitfalls. And I guess if they wrote a paper today in 2017, it would be 50 pitfalls in the analysis of diffusion data. So you have to be a bit careful. It's also not very diagnostic in an individual patient. We see lots of group comparisons where we see significant differences, but there's tons of overlap in the results, and obviously that makes it not usable for a diagnostic single patient application. And there's also a very low effect size in many cases that can't overcome the biological variability or the measurement uncertainty. And you can kind of see that here in this kind of healthy development plot of fractional anisotropy versus age, where there's just lots and lots of scatter. This is 400 people, and if you look at a bunch of 20-year-olds, you can see that there's a range of FA that's quite huge. It spans pretty much, you know, kids as young as 10 to people as old as 80. So how are you going to make use of this in a diagnostic clinical setting if this is the variability you're getting in your numbers? Right? So how do we promote DTI in the clinic? Well, the problem is everyone has their own best methodology, right? We heard it earlier about lots of software packages, lots of methodologies. There needs to be some type of standardization and agreement. And as well, this was mentioned earlier, the protocol depends on the application. If you're scanning kids, you can't put them through a 60-minute connectome scan. If you're trying to implement, if you want to get MP RAGE, you want to get resting state fMRI, you want to get other information, you can't do the best diffusion scan you could ever want. So you have to pick and choose, and that's what makes it difficult to have some type of standardized methodology, right? The one good thing I would say, though, is that new MRI scanners are much better. There's more signal, there's less artifacts, the scans are more robust to motion, so I think we'll eventually, I think, get there. All right, so the last part of the talk is to just focus a bit maybe on the future or some novel methods that people are toying around with. There's not a lot of groups playing with some of these things, but there are things that could be of interest. And I thought for this community, you may not be aware of some of them, so I thought I would bring them up. Obviously, we have, I just mentioned, scanners are getting better. We have higher field strength magnets. We have much stronger gradient coils. We have RF coil arrays that are giving us way more signal from the brain than we could get before. And we get more signal. We can use that for higher spatial resolution. And actually, the greater B values for lower TE are enabled by these stronger gradient coils. And we get a lot more signal as well from that lower echo time. So there's lots of advances that are making some of these other methods a lot more feasible that wouldn't have been just a few years ago. So I'll talk about three of them very rapidly. One is oscillating gradient spin echo, or OGSE. We've heard that earlier today. Diffusion tensor spectroscopy, which looks at metabolites. And then I'll just bring back something that we can all do. This should be 3, not a 2, on high spatial resolution. All right, so one of the key aspects, as we heard earlier in measuring diffusion, is the diffusion time. How long do you let the molecules move around? So let's say we have a bunch of small cells and a bunch of large cells. And if we leave a long diffusion time, the water molecules have a chance to experience all the barriers, and they will be all restricted or hindered. If we leave a very short diffusion time, water molecules that are experiencing will experience barriers in small cells, but may not experience them in larger cells. So it's a way of assessing the size of structures and the size of the barriers. And this was shown a while back in this frog sciatic nerve study, where we changed the diffusion time from 28 milliseconds to 2 milliseconds, right? So most diffusion experiments that you do on your clinical scanner are probably 20, 30, 40 milliseconds, something like that. Getting to 2 milliseconds is very, very challenging on a clinical scanner, but we could do it on this animal scanner. And you can see that the parallel diffusion didn't change at all, but the perpendicular diffusion, when we reduced the diffusion time, increased by 2.4 times, right? That meant the water molecules weren't experiencing the barriers. They weren't getting as restricted, okay? So the ADC that we were measuring was much higher, okay? So indicating that we can then probe different sizes of barriers by altering the diffusion time if we could get really, really low, all right? But that's very challenging to do in vivo. So the method that you can use is this oscillating gradient spin echo method, or OGSE. Here's PGSE, where you just have these bipolar, or these two gradient pulses that are separated by the diffusion time effectively. And then the OGSE, the effective diffusion time, just to simplify, is basically the separation between these two little lobes here. And you can sample the restricting collisions over a much smaller time scale. And people have shown that it's more sensitive to subcellular structures. So a few examples in the literature are on tumors in a rat, where the PGSE doesn't show very much for the tumor, but the OGSE really brings it out. And here in the hippocampus in the mouse, you can get much higher contrast within the hippocampus using the OGSE. So it's giving us new information just from how we're acquiring the data, right? There's no models involved here. We're just acquiring the data in a different fashion. What about human brain? Well, you can reduce the diffusion time, say, from 40 milliseconds, and we got it down to about 4 milliseconds. The only caveat there is that the b-value here is 300, very low, but you could still make the measurements even at a b of 300. And you can see that the parallel diffusion and the perpendicular diffusion both go up, and the FA goes down as the diffusion time gets lower. And that's what you expect, but it's not nearly as much as what we just saw in the frog sciatic nerve, presumably because the axons are much smaller in the human brain. And if we look at the 8 different tracks and we look at the average change, FA dropped by about 7%, going from 40 to 4 milliseconds. Parallel went up 10%, and the perpendicular went up by 25%. So again, as we expect, more change in the perpendicular diffusion than the parallel. And this agrees very nicely with the OGSE study in mice by Agarwal et al., where they saw very similar numbers. So again, it's nice when the human data and the preclinical data kind of agrees. It's a bit of a sanity check that you're seeing something real. So that's OGSE, and I think it's a very interesting method. There's only about 2 or 3 papers in human brain that are published. It's a works in progress. It's available on the Siemens scanner. I don't know if it's available on the other platforms. And so we've been applying it to multiple sclerosis and aging, and we're going to keep trying it out and see if we can use it to tell us more information than what we're getting right now with DTI, with long diffusion times. Another thing, another method 2 that I want to talk about is diffusion tensor spectroscopy. So the problem with water, it's everywhere. It's in all compartments, it's exchanging. What if we could look at only intracellular metabolites like N-acetylaspartate, creatine, and choline? I mean, we're very interested in the intracellular environment. Well, you can do that using spectroscopy. So here's a classic water, color map. You put on a voxel, you get a spectrum. You can see NAA, creatine, choline, myoinositol. This is at a b-value of 347. And then if you go to b-value of 5,000, the peaks attenuate just as you would for water. You can calculate MD, FA, lambda 1, lambda 2, lambda 3, etc. And in this case, we get FAs of around 0.5 for the metabolites in a white matter tract. Okay? But what are the difficulties with diffusion tensor spectroscopy, or DTS? Well, the first thing is that it's got a very low mean diffusivity, it's got low SNR, it has a slow acquisition to make up for that low SNR. Obviously, it has poor resolution. We're just measuring one part of the brain, and then you have to measure another part later, and it's very sensitive to motion. So it's a very challenging kind of method. That said, though, it could be very interesting. These were slides given to me by Itamar Ronan from Leiden, where there's the water molecule, water peak that we get. And if you look at this 1 to 4 ppm region, and now this is at 7 Tesla, or 9.4 Tesla, sorry, You can see lots of stuff that's very interesting to a neuroscientist. There's GABA, there's aspartate, there's taurine, inositol. So you could measure diffusion in all these different peaks, I guess if you have a 9.4 Tesla, and do some very interesting measurements. And, some might be related more in neurons, some might be in astrocytes, and others might be in oligodendrocytes, and start getting that compartmental specificity that we're all trying to fight to do with water. And so the idea is that we've got this NAA or glutamate that's within the neurons, we've got astrocytes, and so on. And so we might be able to get very specific information on a bunch of different things that are very specific to the cells that we are actually very interested in. Okay, so that's diffusion spectroscopy. Last part of this section is to talk about spatial resolution. We've talked about it earlier. Usually people do 2 millimeter isotropic or even worse, basically to go faster, but also to keep SNR at high B values. Like a lot of the methodologies require very high B values, and if you get your voxels too small, you lose all your signal. So people like big voxels, and then they use the modeling to kind of try to sort everything out. Nowadays, I think with the phased arrays, the higher fields, even at 3 Tesla, this works all on a 3T, our standard approach is 1.5 millimeter isotropic, which is an almost 2.5 times smaller voxel size than what's standard, and you can still get 3 directions and so on in 5 minutes and get full brain coverage. And if you zoom in, it still isn't the greatest thing in the world to have 1.5 millimeter isotropic, right? But it's still a lot better. And especially if you're interested in smaller structures, cortical areas, subcortical gyri, etc., it makes a big difference. And I'll just show you kind of a more extreme example here. This was work presented at ISM-REM just recently on the hippocampus. There's lots of interest, obviously, in the hippocampus. People have measured diffusion abnormalities in dementia, epilepsy, ALS, etc. And the problem is that people have acquired whole brain protocols with low resolution and then measured the hippocampus. The problem with that approach is it's not dedicated for such a small structure, and so it's not optimal, right? So if you look at a 2 millimeter isotropic data set and you look here at the hippocampus, it's pretty low res. You don't see a lot of structure there, especially if you're interested in subfields and that kind of stuff. So can we do better than that? Sure. So these are 1 millimeter isotropic diffusion weighted images, just using single shot EPI that's just available on your scanner. We use a low B value to get more signal, and it took about 6 minutes. We only acquired 20 slices, and these are a different orientation that you might be used to looking at it. It's aligned along the length of the hippocampus from front to back. And now look at all this beautiful structure you can see within the hippocampus. You can see digitations in the head. You can see the SLM going up there. You can see distinguishing between the amygdala and the hippocampus, and so forth. So you can get some very nice anatomical detail if you focus your diffusion acquisition on the structure that you're actually interested in, and then you can make diffusion measurements and so forth. In addition to that, you can look at variability between individuals. These are 4 healthy adults, and you can see lots of digitation here, less so there. This one's very smooth. This one's got some more digitations. And start looking at variability, because now we can actually see something, okay, and make measurements instead of the blobs, right? So I think this will be a very useful strategy going forward in terms of diffusion imaging. And then this is another example just at 0.8 millimeter isotropic or 0.5 millimeter cubed, where you start seeing striations in the hippocampus and some real beautiful structure. The unfortunate part about this scan is it took 34 minutes, but still half of the connectome scan, so not too bad. So hopefully I've just shown you a few different things. It covered a lot of ground in 33 minutes, a little over, about determinants of anisotropy. It's led to different preclinical models to examine that. We've looked at clinical applications, post-processing advances, fitting models, novel diffusion acquisition. All these things kind of feed each other and have really moved the field forward. And I think the future years are very exciting indeed. If you want to learn more about diffusion, we have these workshops every few years. This was in 2002 in Saint-Malo. This was in Lake Louise in 2005, Croatia in 2013, Lisbon in 2016. You can see that diffusion people like to go to nice places. So in a few years, there'll probably be another workshop, and if you really want to learn more about diffusion, I would encourage you to keep an eye out for whenever the next one's going to come out. And thank you very much for all of your attention, and Flavio and the organizers for inviting me.
Well, Christian, Beaulieu, thank you very much for this interesting wrap-up of our diffusion educational course. Your contribution was the last, but definitely not the least. We were very excited when you said you're contributing to our educational course. At the end, the next 30 minutes, we have a question and discussion section, so you can ask all presenters of this afternoon session, and we are happy to respond to your question. If available, you can also ask questions to presenters of this morning session. They are probably also happy to join in case needed, but let's focus on the afternoon. Do you have any questions?
Hi, thank you very much for interesting talks. I was wondering about track-weighted imaging. Do you have any recommendations for the acquisition, for example, so on whether that would work better with certain types of resting state or certain types of B values, multi-single shell, and more of that information?
Now it's working. So the track-weighted, for the point of view of the structural connectivity, we pretty much use the tractograph. So the better the tractograph, the better the image. So the acquisition, answer the question would be, what is the good acquisition for tractograph itself? So I would say, for example, typically you would use a high B value to be able to resolve crossing fibers, something like 3,000, and multiple directions, like something like 60 or so. If you can do multi-shell, you can start doing multi-tissue things and resolving things like that. So whatever gives you a good tractogram, that acquisition would be like that. So as I say, for clinical studies that we use is typically 45 to 60 directions, p-value 3,000 will give you good results. For the resting state, is whatever is good for resting state. Typically, you would want long data sets, but for clinical studies, we don't have that time. So typically, we do anything between 7 to 10 minutes or so. That gives us good results. But in some ways, it's a question. It's a tricky answer even for functional connectivity itself. But we're finding that those type of protocols are enough. It's not very obvious at the moment we don't have enough experience for the multi-band that you can acquire more data points. But then there is a question: is how much time dynamics and things like that. You want enough time to see those dynamics. So it might be that it's not going to cut down the time for the functional connectivity that much. But we don't have enough experience of that yet.
So do you have any idea whether there's a trade-off between the two? Because I can imagine if you're going to do some track weighting, that your resting state data is, for example, of a much better quality than your diffusion data. Or
yes, so from my experience, the key one is the fiber tracking, because you're going to be propagating things with that tracking. The tractogram is not good quality. You're going to get completely rubbish results because you're propagating information. The functional connectivity, we tend to, at least if you do, the standard deformal network, any language paradigm, things like that, you have very big blobs that they're very well defined with those types of acquisitions. I think if you start going to networks or data that is more specific, looking at very specific areas, then, the functional connectivity, again, you will have to be very careful, get very optimized protocols there. But for the standard things, the key one is the tractography. Yeah. That's our experience.
Maybe I jump in here. You're using probabilistic tractography tracking with matrix, as much as I remember. Yeah. Might be an important aspect.
I have a question regarding diffusion imaging acquisition. So as you know, there are so many acquisition sequences available, like Hardy and diffusion TTI, and also recently like a human quantum project, right? So we try to follow up HCT sequence. They use 3 shells, but unfortunately, so it'll cost you 1 hour to get a TTI data. So, and also recently ABCD studies, right? So they use another DTI sequence, 5 shells. So and they use called the DSI model. So do you mind tell me which model should be standardized, or there's no standardized DTI sequence, and also data processing and analysis model?
I don't know if I can start taking that answer. So I think there is no one answer, one protocol is going to help for everything. It's going to depend on the application. Like, for example, for DTI, there is no point in acquiring 5 shells and an hour acquisition, if you can do it with very short things. So.
Okay, so my application will be, for example, I want to do a longitudinal pediatric study, right? So now HCB, of course, doesn't fit my study, but I try to follow an ABC study. But ABC use 5 shells. I don't know what's the reason. Instead of use 3 shells or 4 shells, there's a literature. Suggest how many shells will be and how many DTI directions will be for each shell.
I'll make one comment on that. That a lot of times we want to say that one algorithm or one acquisition is the best, but I think in reality it depends on the research question. So I scan kids, and I work with the time constraint of how long a kid can stay in the scanner before they start moving. So I have to think of research questions where I think I can get enough measurements to answer my question in the time constraint that's presented. So even though that's not a clear answer on use this acquisition, you can read through the literature and select, optimize for your application. So for example, if your goal is to get tissue properties in a multi-compartment model, then of course having multiple shells is going to matter a lot. Whereas if you really need accurate tractography to map endpoints of fascicles, then having a higher angular resolution, maybe a higher B value is going to matter. So it really depends on the specifics of the research question.
I can just give you what we're starting a new study on kids and so forth, and just like you just said, we have time constraints. I need MP-RAGE, I need some QSM, I have other things I want to image as well, and I have maybe 25 minutes total for everything. And so what we've decided at our site is we're just going to do B1000 30 directions, B2000 30 directions, and with simultaneous multi-slice, I'm doing 1.5 millimeter isotropic, 90 slices, and I can do that in 6 minutes. So that's what we've decided for us is going to be our protocol. Now, of course, will we be able to do a lot of the other algorithms that need higher B values and so forth? No, but I can get a lot of information out of that data set. I can get kurtosis, I can do crossing fibers, and so I think it's a good compromise. And I'm still getting higher spatial resolution, which is something I think we should take advantage of with the greater signal that we have on our new systems, especially if you're not going to extra high B values. So anyhow, that's just my personal.
And one final comment regarding whatever protocol you choose, you had to be smart at how you choose the, for example, if you're going to do a fiber tracking experiment or whatever, your directions regarding motion, because if you're going to take, for the sake of argument, 5 directions and you do that one, that one, that one, that one, and that one, and the subject move after that one, then you suddenly didn't sample that. So, there are strategies that or the same multi-shell, you wouldn't acquire one shell, and then, there are ways to do it. So if for anything there is motion or something, you still get enough data to reconstruct something. It's not the whole thing thrown.
Yes, in terms of I'm not sure on other people's questions. I don't want to cause too much time, but it's a very interesting topic, So this afternoon, so the speaker shows, tractographic difference using streamline-based and the probability-based, right? So, but we don't know which one. It's a better than another one compared with one shows. So, for example, even for the probability, tractography, sometimes different toolboxes give you different results. So my question would be, so in the DTF, data processing and the analysis field, actually it's difficult to standardize. And also, is there any way to quantify for each findings? That's my question. Because recently I analyzed many studies of DTI data, but unfortunately I found, it's a trick sometimes, You adjust the different parameters and you use different models, you get different results. So, but how can you interpret your findings? That's open field.
Yeah, I mean, this relates a bit to something we discussed earlier in the morning at the question time. There is no gold standard for many of these measurements. So, unfortunately, it's not that we, other parameters, other MRI measures that you have gold standards. You can say, well, you choose the protocol that gives you the closer to the answer. People have tried things. Well, which one is the one that gives you the better reproducibility and things like that. But for example, if the criteria is reproducibility, you can have the wrong answer very reproducible, but it's not the way to go. So unfortunately, in this field, for many of the things that we measure, we don't have a gold standard, and then it's very hard to come up with what is the best way or the right way to do. And that's why the field hasn't agreed on what is the best way to do.
I might jump in here a little bit. There is no fixed standard that I agree, but there are some rules of thumb that are founded on empirical observations. For instance, on the number of diffusion gradient directions that you should do. But it depends on the model. If you're interested in the tensor model, then, for instance, the minimum according to the math is 6 directions, but the optimum is something like 30 directions. There's a publication by Jones, I think 2005, I can look up, which says that you get improvement in the signal-to-noise ratio up to about 30 directions, but afterwards it's asymptotic. So based on that, I would suggest if you do tensor model, use 30 directions. If you go with the ball and stick model for fiber tracking with FSL, probabilistic fiber tracking with FSL, then you usually want to model at least 2 anisotropic compartments per voxel. If you want to do that, then there is a publication by Behrens, 2007, I think, that suggests that the minimum in order to be able to model 2 anisotropic compartments is something like 30 directions. It's better to have more directions, but that would be the minimum. So it depends on what your model is. If you go by the Naughty model by Gary Zhang, he has published some optimal protocol for the Naughty model, which is based, I think, on 3 B values and a set of optimal diffusion gradients. Contact Gary Zhang for the optimum sequence of the Naughty model.
Great, thank you. So last question. So regarding the opposition, right? So recently I tried to do a retest. For the DTA data. So that's why I want to use phantom. Do you guys have any suggestion to acquire what kind of phantom should I use? Because there are many DTA phantom available in the market, So I'm not sure what kind of phantom did you use. Especially for the cross-size studies, right? So you have different size. Then how do you make sure different size will acquire exactly the same DTA data? Then you do multiple comparison in the future.
I'm not familiar. Yeah.
I mean, there's different. I think one of the studies was using some type of iced water phantom. I mean, you can use a phantom where you expect a certain diffusion coefficient, and you get that out. And then the problem is if you have an isotropic phantom, you'll get the low FA value, but you're mostly looking to get the mean diffusivity is all equivalent, and then assuming that your gradients are performing fine, everything's still working. And so there are other chemicals as well that have ADCs of similar to human brain around 0.8. So there are some available as well. I can't remember what it is off the top of my head, but I don't think there's any standard that everyone uses, obviously, because no one's jumping up and saying, "Oh yeah, this is the one you use."
Because NIH recently released a new one. I'm wondering if there will be a gold standard in the future. But anyway, thank you so much.
Thank you.
Yeah, I was curious about your functional connectivity weighting your tractography. If you've looked at how to incorporate those indirect connections that are communicating with that extra node.
Yes. So there was something that we discussed briefly in that paper, and people have done it for other things, for the just the connectivity matrices. That is, in very simplistic terms, what you can do is if you have a streamline that goes from A to B, you can take another streamline that goes from B to some other place C, and then do the correlation between A and C. So do another second jump and things like that. So there are tricks that you can do like that. But in many of those studies, what they found, not related to track weighted, but for the connectivity, is that the second order connections, they do contribute, but still the direct connections are the major ones. So it's something that we thought we're going to explore and all that, but we haven't had a chance yet to see how much effect that it has. But that would be the avenue that we suggested it would be the simpler way just to add, if you wanted to jump to two streamlines, and then you create like a fictitious one stream by concatenating those two, and then you're looking at those two endpoints and things like that.
So what kind of decisions did you use to maybe find that middle ground, I guess, or the middle node?
The second one, no. So what you need to do is, if I'm trying to think now in my head of how you would program this, is you would get your, 10 million streamlets. You would go one by one of those ones, find the endpoint of that one, and choose one that this another one that has an endpoint closer to that one, but ends in a farther distance or a different node or something, and concatenate those two. And since you're doing this in a probabilistic frame and you have millions of these ones, so you probably have to do that only once. It's not that you have to repeat it many times, because by chance you would, another streamlet would choose a different one and so on. So that's, I'm thinking you would do from a programming point of view, it would be something like that. But although we discussed it that we're going to do it now, 2 or 3 years ago, at the end we never ended up doing it.
Yeah.
Mm-hmm.
Thank you.
Thanks.
Hi. Could you comment, please, on the usefulness of these techniques in the midbrain brainstem, say with 2mm resolution?
Are you asking any in particular, or diffusion MRI in general?
Yeah, diffusion MRI with tractography combined with fMRI.
Oh, so it is the combined instruction function. Tracking you can do fairly well in brainstem, and people have shown, I didn't talk here, but one of the things that we did in the last few years is the track density image. This image is to use a tractogram to look like a histogram of a tractogram, and you get fantastic anatomical detail in the brainstem structures. Functional connectivity is not, it's going to be, might be tough on how you said that, because the functional connectivity might not be as well there. So I don't have any personal experience on that, but I think the problem will be in the functional side, not on the structural side. That would be my guess. But as I said, I don't have any practical experience on that.
Thanks.
So, but the structural connectivity is very, very good in there. You can get very good results with good methods on the brainstem.
So I know you already kind of touched on this earlier with the indirect connections, but I was just wondering about when you have the first version, when you have a network and you have the bold signal, but then you can't find a direct structural, how does it handle that? Does it just give up on that one, or?
Sorry, the last bit, I missed the final bit. There
No,
was a
it's
question.
Okay. So when two places are structurally connected, but
Yes.
functionally connected, but it can't find a direct structural connection,
Mm-hmm.
what does the output look like from that? Is it just nothing anymore?
Yes, so this is for the first method, the one that used the network. Yeah, so in that one, in those ones, it was completely unconstrained. So you would have one of the things that we showed that it was nice in our data set, for example, the deformable network, we didn't detect, because it was not enough number of subjects, the nodes that they were down in the hippocampus. But still, by using the other nodes and in an unconstrained way, you did find the track weighted had pathways going all the way to those ones. So in some way, it needs still to have a direct connection, because it is looking at, you assign a value of weighting to each streamline in the brain for that method. So in that one, it would be very hard to imagine how an indirect path would take place, because it is not part of that. You're just saying, I have these networks and I'm going to let them propagate in my function. So in some way, it only works for direct connectivity, that one. The first method is only the second one, where you're looking at endpoints where you possibly could extend it to second pathways, direct, indirect pathways.
Okay, we had a lot of questions about functional connectivity and structural connectivity. Right now, there's no question from the plenum, and we still have a few minutes' time, so I take the opportunity to ask Beaulieu about this novel thing about diffusion, MRS. One problem with MRS is that the molecules are relatively sparse in the brain. So the question is, how likely... how do you see the chances that this will actually be clinically relevant in the future, given that the signal-to-noise ratio, because of the limited number of molecules, is limited? Do you see some developments that this can be relevant in the near future or far future?
Well, I mean, I think it's DTS. I mean, we kind of talked about how DTI is still not really made it to the clinic, and it's been, 23 years. And so the DTS stuff is there's just there's a handful of groups in the world kind of working on it, trying to improve the methodologies to make it more robust. One of the things our group's trying to do is that often you'll get a voxel and it might take, and you do multiple B values, multiple shells, and averaging, and it might take you 20 minutes or 30 minutes. The original paper we had in 2006, the whole scan, including eddy current and everything, was 80 minutes long, right? Obviously not feasible. So lately we've been, at ISMRM, we just presented a poster where we can do everything in about 5 minutes. So then it becomes more clinically feasible. I mean, you have to limit yourself to 6 different directions and so forth, the things that are unpopular in water, but are a necessity for metabolites. And with more sensitive coils, higher fields, I think everything coalesces to make it a feasible technology. I mean, I didn't mention it, but the original paper that introduced the concept was in 1993. And then people kind of forgot about it and then started doing it again in the 2000s. And there's a few group, like Inamar Ronan's group, that's pushing it, and they're trying it out in different patient groups to see what other information could the metabolites show you that's not being shown by the water. So I think we're at that stage where we need to demonstrate, A, we have to get the acquisition time down, and then B, we have to show what is it useful for. And I think the jury's still out for that.
Okay, last call for questions. I don't see, one more.
Just if there are a couple minutes left, I was kind of curious to hear people's thoughts about, we heard a lot about sort of the importance of pre-processing and obviously interest in various sort of clinical populations. And so I was curious about hearing people's thoughts on normalization, for example, in multiple sclerosis and so on, where you might not be able to use some of these surface-based methods because a lot of the lesions are sort of in subcortical regions where you'd really like to sort of look at this. If anybody has any sort of recommendations in terms of how to deal with nonlinear normalizations in patient populations with subcortical lesions.
That is difficult. I think it causes problems with all types of procedures. The surface reconstruction might be altered. The nonlinear registration to a standard brain might be altered. And also the TVSS tracts might be altered by that. Nevertheless, you can try. But I think if you have the luxury of having good anatomical hypothesis that certain structures are involved, I would try in your case to segment these structures, the subcortical nuclei, in each individual brain. And in this case, I think a ROI analysis, even though relatively old, may still be one of the best way to go. So definitely you should supplement your analysis with a ROI-based analysis. That would be my recommendation on that. Whether it's possible to do this automatic fiber quantification with the Dietmanners, then depends on the type of fibers you're interested in. Maybe they are still preserved and can still be tracked, and then you can still do some quantification on that as much as I know the method.
Yeah, I would say there's a big benefit in patient populations about working based on tracts identified in individual brains. We found even in cases with severe structural abnormalities, you can usually still find the tracts in an automated way, and they still can be lined up if the tractography is done in the individual. So,
I guess the only problem with that might be, for example, if you have an MS lesion, and if the automated fiber quantification relies on the tractography is likely to fail at the site of the lesion. And precisely what you might want to quantify are the differences between some quantitative measure like FA or MD or something like that in the lesions themselves. And so it's a tough problem. I was just curious to hear your thoughts.
I think it also depends a little bit on the severity of the problem. If the integrity, the problem, the sclerosis is relatively mild, you can still perform the tracking. When it's severe, then the problem fails. Okay, I don't see any question anymore, and it's also time we need to stop here. So thank you very much for the speakers. Thank you very much for being here. It was a pleasure to be with you, to talk about diffusion from the basics to the advanced. And so it's my duty now to also on behalf of Flavio Dell'Acqua and also on Alfred Anwander to close this session. I hope you got something out of that, and I'm confident that you got some relevant information that you can use for your future research. Thank you very much.
And please give us feedback in this feedback sheets that you can fill out to have some information for next year. Thank you.